Good morning, guys and girls. I'm Francesco. I'm a chemical specialist and I've got a master's degree in industrial chemistry. Today, I want to tell you something about detergents, explaining how do they work and how they are made. So, let's start. In the common language, maybe you've heard terms such as detergent and cleanser used as synonyms, but from a chemical and industrial point of view, these two words have a different meaning. Detergents and cleansers have in general the same aim to clean something that can be the human body or any other object, from clothes to things like cars and the windows of your home. In general, detergents and cleansers cover the macro category of surfactants. This strange word is the combination of the abbreviation of these three following words: surface active agents. Okay, but what about the meaning? Yesterday you bought the shirt you dream so much because the fabric is very soft, and this evening you go out with your partner for a dinner at the restaurant. You order a pizza and it comes at your table with a lot of oil. You, who are hungry, put a piece in your mouth and a little drop of oil falls on your shirt. The damage is done. Oil stain will remain on your shirt all the evening until you get home to put it in the washing machine. So, starting with this common misfortune, we can think about where the stain appears. The latter appears on the surface of the object, and yes, of course, it can penetrate. There are different types of stains. From a chemical point of view, this can be polar, non-polar, or both. At this point, we can remember the famous sentence widespread in chemistry, like dissolves like. It's a good rule of thumb that can be interpreted, such as polar substances can dissolve polar ones, non-polar substances can dissolve non-polar ones. In general, it's not common that polar substances dissolve non-polar ones, because they have a different affinity. Starting with this milestone of chemistry, we can imagine that cleanser and detergents, to remove dirt of different nature, they must be endowed with a dual nature, polar and nonpolar. The formulation of cleaning products is strictly dependent on the nature of the dirt to be removed and the object that needs to be treated. Most of the commonly used objects can be treated with an APCI, which stands for All-Purpose Cleaner, a versatile and no-too-much sectorial cleaning mixture. On the contrary, objects such as fabrics, silverware, surfaces lacquered and painted, glass and lenses, wooden, antique objects require detergents specially formulated. At this point, we can make the first distinction. We can define a cleanser such as a mixture of surfactants and other specific components, so it's a word with a broader meaning. Instead, a detergent is defined as a cleaning product, not necessarily containing surfactants. In the common language, detergent is the most used term regardless of the context. Formulating a cleaning mixture for fabrics and fibers is one of the sector of chemistry more elaborate, closer to the consumer. A detergent for cleaning a fabric must satisfy a primary function, the removal of the dirt, and a secondary function, which includes the care and the preservation of the fiber. Let's pay attention to the primary one. Dirt in general can be divided into two categories: hydrophilic dirt, such as salts, sweets, sugars, and urea, and hydrophobic dirt, such as grease, proteins, carbohydrates, fruits, vegetables, wine, coffee, limestone, rust, oils, and mud. In particular, dirt made from carbohydrates and proteins is called enzymatic dirt, since it requires the use of enzyme-based detergents for its degradation. There are many substances that are called oxidizable, typically very colored and persistent, which are difficult to remove, and a very common way is to oxidize them by using depletion systems or lightening agents. In this way, of course, the stain remains of the object, but the human eye cannot longer see it, because when the molecules which the stains are made of are oxidized, they break in small molecules, shifting their emittance wavelengths outside the visible region of the electromagnetic spectrum. If you don't know anything about light and electromagnetic spectrum, or if you're curious, you can watch my video both. It's in Italian language. If you don't understand Italian, you can use YouTube captions. Let's carry on introducing the second function of a detergent, which involves the preserving the quality of the fabric and the creating an appeal of the product toward the consumer. The detergents must first avoid the felting and the packing of the protein-based fibers, such as wool and silk, and the decrystallization of cotton to form lint and fiber balls. In addition, the cleanser must avoid as much as possible the redeposition of the material during washing of newly removed dirt or of limescale present. Similarly, the cleaner agent should not attack the metal or plastic parts of the washing machine or washer system. Secondly, the foam produced during washing must be adapted to the circumstances. An hand washing soap is generally more appreciated by the consumer if it does foam and smells clean, while a detergent for industrial use for washing a machine must not produce too much foam to avoid spills and inconveniences. From the point of view of the fibers to be treated, each fabric has a certain characteristics that require specific treatment, both in terms of temperature and action bleach. Natural fibers such as linen, cotton, and hemp need high temperature and strong bleaches. Protein fibers such as wool and silk need low temperature and not bleaches. Instead, artificial fibers like viscose and acetate need low temperature and no bleaches. Synthetic fibers, for example nylon, polyester, and acrylic, need low temperature and moderate bleaches. Finally, the detergent must meet the demands of the consumer, requests greater performance of the product, for example, using 30 degrees for quick and economical washing, and cannot no longer rely on old methods, such as washing at 95 degrees or boiling. The detergent must thus be able to obtain good results at low temperatures in short and moderate action times of mechanical action. During the washing, surfactants carry out different actions. The first one is wetting. By reducing surface tension, they allow the mixture to wash permeate into water-repellent fiber, solubilizing, emulsifying, and dispersing. Thanks to their amphipathic characteristics, they remove and solubilize the fat particles and allow the washing system to move them away from the fabric. Foaming or anti-foaming, depending on their intrinsic chemical characteristics, surfactants can produce or limit the production of foam. Softener, antistatic, corrosion inhibitor, and bacteriostatic. Surfactants, especially cationic ones, can also perform these functions. Additional care and conservation measures for both the fabric and the washing system. An amphipathic molecule is a chemical species composed of two portions with marked difference in polarity. All surfactants consist of a long nonpolar tail, like another carbon chain or a fluorocarbon chain, soluble in an organic environment but not in water. Then there is a more or less long polar head, insoluble in organic phase, but soluble in water environment. The head generally confers water solubility to entire molecule. For example, cetyl trimethylammonium bromide (CTAB) is a surfactant formed by a 16-strand nonpolar tail carbon atoms derived from cetyl alcohol and a polar head made up of ammonium quaternary positively charged. The polar heads can be more or less charged or polarized. Surfactants then orient themselves to orient the hydrophilic heads towards the washing mixture and the hydrophobic tails towards the greasy dirty particles or the surface in contact with the air or with more nonpolar materials or other surfactants present in the system. The interfaces and contact surfaces between two different phases are therefore subjected to less surface tension. When a surfactant comes into contact with water, the hydrophilic part is solvated, so water molecules surround it, while the hydrophobic one is not. It follows that its solubility depends on the energy balance between the parts polar and nonpolar. If the nonpolar part is sufficiently long, the molecule tends to arrange itself on the surface by keeping the polar heads in water and the hydrophobic chains aligned in the air. This arrangement decreases the surface tension of the water, hence the name of surfactants. The reduced surface tension is the cause of the easy formation of bubbles and foam. If the concentration of the surfactant is sufficiently high, the surface is saturated and a new arrangement develops, the micelle. This is located in the bulk of the solution. It has an almost spherical shape, and it has the hydrophobic chains all facing inwards, and the polar heads remain solvated. Water is excluded from inside the micelle. Every micelle contains from a 40 to 50 or to a few hundred molecules, and its size is sufficiently big to diffuse the light, so the solution becomes opaque. Thanks to this strong tendency to orient themselves towards materials of similar polarity, a surfactant and a concentration can easily form micelles. The critical micelle concentration, CMC, indicates the concentration at which the surfactant ceases to be present as an individual molecule in the system and instead begins to self-aggregate into micelles. Generally, beyond the CMC, the surfactant no longer contributes significantly to the lowering of the surface tension. Despite this, since it can be lost in the washing environment due to the adhesion to other surfaces, solid particles of dirt, dust, ionic species, or impurities in the water system, a value higher than the CMC is used, though the real concentration, lower than nominal, is still effective. The wetting action mentioned previously is the qualitative manifestation of the lowering of the surface tension of the washing solution in contact with the material below a critical threshold. The liquid spreads and permeates into the fiber. The rolling up phenomenon, the removal of ball of greasy dirt, also occurs due to a lowering of the surface tension between the two phases. Finally, emulsification uses the micelles to incorporate and remove the small ones dirt particles after their removal. Quantitatively, a drop of liquid in contact with the surface has an angle of contact, which helps us to understand how wet the substrate is. In the case of washing water that must work with fabric, it is desirable having an angle or as much as possible minor than 90 degrees. Ideally, with an angle equals to 0 degrees, the surface is totally wet. In the case of the fat particle linked to the wet tissue, the best situation occurs when the angle is greater than 90 degrees and the particle is therefore partially detached from the substrate. The contact angle in an equilibrium situation is related to the force that binds liquid and the surface. It can be quantified simply by Young's equation classical, where the y's are the tensions at the interface between the phases, fabric, stain, and solvent. In a realistic non-equilibrium situation, with a fabric wet from the aqueous washing mixture and covered by a nonpolar spot, it's observed that the increase in the contact angle is also caused by the action of the surfactant that surround it and put it away in an emulsified mechanism. The wetting of the fabric, however, modifies the balance of interface tensions and causes the lithophilic stain on the wet tissue. When polar solution takes on increasingly largely contact angles, become balled up or rolls up on itself until it is then removed by the mechanical action of washing and emulsifying behavior of the surfactant. Surfactants are commonly classified based on the chemical nature of their hydrophilic head. Anionic surfactants are negatively charged and useful for information and regulation in the removal of stains and dirt. Cationic surfactants are positively charged and they are useful in bacteriostatic and softening agents, also for removing dirt. Ampholytic and amphoteric surfactants are foaming agents with a delicate cleansing action. Non-ionic surfactants regulate foam and remove stains. The surfactant is selected based on production and consumption requirements. A substance is a good surfactant when it has an high absorption and resistance to water hardness, desirable and controllable foaming properties, high power wetting, and high solubility in the detergent mixture of the washing environment. The requirements more linked to the characteristics and formulation of the finished product are low toxicity and high biodegradability, the absence of odors and colors intrinsic to the molecule, the low price and the high availability, stability for long medium-term storage, and of course be easy to use. A cleanser doesn't contain only surfactants because there are other substances important to enhance the quality of the washing. Colored stains are usually caused by chemicals with conjugated double bonds, as in the case of zeaxanthin, a yellow carotenoid from the xanthophyll family, and the main yellow coloring of egg yolk. These molecules have the characteristic of absorbing heavily in a UV visible region. They are therefore strong and persistent chromophores that bind so firmly to the fibers that they sometimes can only be whitened and not be removed. Specifically, the bleaching of these molecules consists in the destruction by oxidation or reduction of double bonds. Bleaching, through reductive processes, uses reducing agents such as sulfides and acid sulfides, thiosulfates, and other sulfur compounds with good redox chemistry. These treatments involve, however, unpleasant odors and vapors, and are therefore relegated to industrial bleaching. For example, in the paper and the cellulose industry, oxidative processes are much more common and easy to manage. The main challenge is to succeed destroy unwanted stains without affecting the dyes of the fabric, which are obviously also chromophores and often very rich in functional groups or heterocycles reactive to the reactions of oxidation reduction. Furthermore, an oxidizing agent must whiten without ruining the fabric. The most common oxidizing agents for whitening and cleaning are mainly three: sodium hypochlorite, dioxide chlorine, and hydrogen peroxide. The sodium hypochlorite is a strong oxidizing and bleaching agent. It's used exclusively for cleaning and disinfecting surfaces and environments, as it destroys many organic dyes and ruins fabrics of natural origin. Dioxide chlorine is a strong oxidant and it is used only in water treatment. Chlorates and perchlorates have no civil or domestic use. Hydrogen peroxide. This is a common oxidizing agent, often added as an additive in liquid whitening formulations in acid solutions. It is unstable in the presence of some surfactants and in an alkaline environment, in which it tends to decompose to water and hydroperoxide, and it is therefore difficult to store. In reality, in Europe, 45% of the hydrogen peroxide produced industrially is used for the production of the perborate and the percarbonate, products intended for those uses where it cannot be bleached with sodium or calcium chloride and hypochlorites. Hydrogen peroxide and sodium bicarbonate, beyond their oxidizing action, require the presence of a bleaching activator that transforms free peroxide into peroxy acid, especially more oxidizing and reactive. The using of an activator allows the improvement of the whitening action and the lowering of temperature and washing times. For example, one of the most common activators is tetracyl-ethylene-diamine, TAED, not to be confused with tetracetic ethylene diamine acid, EDTA. The activating action of TAED occurs through the attack of the hydroperoxide ion on the carbonyl carbon, with formation of a peroxy acid and diacetyl diamine, DAED. The TAED finds its maximum efficiency peak at 60 degrees. It is safe and does not affect the rubber and the metal portion of the washing machines. In addition, the peracid produced has also biocidal effects. More widespread in the USA and Japan, countries with different laundry habits, are derivatives of p-nanoyl oxybenzene sulfonate, NOBS. Used at low washing temperature and irregular cycles, they have also excellent surfactant action on greasy spots. Their poor diffusion in Europe is due to the fact that if they are used in long washes and at high temperatures, they tend to stick to be absorbed to the rubber parts of the machines, damaging them. Even the case of NOBS, activation occurs through the formation of a peroxy acid. Photocatalytic mechanisms based on sulfonated zinc porphyrins are also known and exploited when drying hanging laundry exposed to the sun. It absorbs oxygen in the triple state that is then converted from the sunlight to the singlet oxygen, which oxidizes and whitens the fabric. Excellent catalysts for removing stains and dirt of organic origin are enzymes, protein especially created to withstand washing environments. Enzymes are characterized by a specific three-dimensional structure that binds selectively with a hand-glove mechanism some classes of molecules. Stains from protein compounds, such as eggs, milk, blood, are difficult to remove because they adhere strongly to the fiber. A proteolytic enzyme hydrolyzes proteins and allows them to be removed. The first enzyme containing product appeared in 1913 in Germany, and it consisted mainly of sodium carbonate with animal pancreas extract. The action of the enzymes was originally confined to pretreatment of tissue overnight. In reality, the enzymes in cleansing formulations have evolved greatly since their entry into the world market, and now they are able to carry out their action even in a short time and temperature up to 60 degrees and at a fairly basic pH. Furthermore, by their nature, they are completely biodegradable and given their specificity, they are used in mixtures to attack a large variety of stains. The enzymes, although sometimes modified with genetic engineering techniques, still work to moderate temperature and pH. There are various types of enzymes: proteases, amylases, lipases, cellulases, mannanases. Adjuvants and alkalis are substances added in large quantities, sometimes as fillers, to the cleaning mixture. They have a primary and secondary function. A primary function is to avoid the reduction of the detergent power and other cleaning substances, for example, by reducing water hardness and sequestering divalent ions. The secondary function is to avoid the formation of deposits and incrustations on the fabrics, typically preventing the formation of insoluble inorganic or organic salts. Zeolites are aluminum silicates with a three-dimensional tetrahedral framework containing cavities occupied by ions and water molecules with high mobility, such as to allow ionic exchange and reversible dehydration. Zeolites require polyacrylate carriers to be well dispersed within the washing system, and they are divalent ion sequestrants with high selectivity for cadmium. They are not suitable for liquid formulations and must be carefully dosed. Polymers can regulate the viscosity. In a cleanser, the viscosity has a significant importance because the consumer often associates a viscous liquid as an high quality and quantity product. Polymers help sellers from this point of view. The market for detergent polymers is dominated by polycarboxylates. In first place, with a 71%, followed by carboxymethyl cellulose (CMC) with 21%, and polyethylene glycol 6%. Polycarboxylates are solids or liquid species produced from polymerization of carbonyl monomers of acrylic acid and malic acid. They have a low toxicity, but they are poorly biodegradable and they can be exploited in synergistic action combined with zeolites. They can change the rheology of the system and modify its viscosity, even at low concentrations, by changing the pH of the washing mixture. When carboxylic groups become negatively charged, the polymers move away from each other, modifying the viscosity of the solution. Now let's see the secondary action additives. Fabrics, especially cotton, tend to become slightly yellow with wear and age. This is due to a modest absorption in the visible blue-violet, which gives it a yellow tinge. To remedy this phenomenon and bring back cotton to reflect 100% of visible radiation, you can add optical brighteners on complementary dyes. Optical brighteners are organic conjugated molecules, slightly coloring, which absorbing in the UV and emit in the visible blue, and in addition, they counteract yellowing. There are two types, stavonyl and distyrenyl biphenyl derivatives. Another characteristic important to induce the consumer to buy the cleanser is the perfume. The latter is obtained with the use of fragrances, which are mixtures also containing several dozen synthetic molecules that come designed to make the product more attractive to the consumer. The substances used are generally alcohols, esters, ethers, terpene compounds, aldehydes, ketones, inspired by the animal and plant kingdom, but of synthetic origin. Fragrances are divided in numerous notes, but in general, they are structured and designed according to the pyramid scheme. The top notes are very volatile compounds and determine the first impact on the consumer who smells them. The middle notes are less volatile substances that vanish shortly after the garment dries. The bottom notes are low volatile substances whose clean scent lasts for a few days or weeks. These are all the substances present in cleanser that we use almost every day. Thank you for watching my video. If you like it, please give it a like and subscribe to stay updated for next videos. See you soon. Bye from Frank.